to start way at the beginning. Okay, identify where our reactivity is located. We've got reactivity on A, our carbon A, which is blue there, and in structure B, we've got it at both those carbons with the alkene. Okay, so we're just trying to identify those positions. Okay. Are there any constraints on sources? Well, I'm lazy, so I never really give you a constraint, so we don't have to worry about that. And then major functional group changes. What happened to our functional group? We went from an alcohol to an alkene. Okay. And we'll worry about that next one in the next part of this. We'll try and get the first part first. Identify the carbon skeleton. Where's our carbon skeleton? We'll go to A to B. It's the exact same. Our carbon skeleton doesn't change, so that's kind of nice. And then do we have to move reactivity? Yeah, we really do. We're looking at a pretty significant shift of that reactivity. Okay, so now where do we start? Do we want to work backwards from B or forwards from A? All right, I heard forwards from A. What do you want to do? Okay, how do you want to lose the alcohol? Okay, why elimination and not a substitution? We're trying to work towards our product, our B product, which has the reactivity inside the ring. If we do a substitution, that's fine, we can do that. There's nothing wrong with doing a substitution, except does that get the chemistry into the ring? No. So what we really want to do is try and get it towards the ring. So somehow shift our reactivity inwards. All right, so how can we do that? Came up with the idea for an elimination. When we do an elimination reaction, typically, what do we need to use? Strong base. All right, so let's write that down as our first thought, or our first thought. And we would hope that we would end up with our elimination like that, right? If we had a strong base, what's it going to react with? Hydrogen. What hydrogen? What hydrogen do we want it to react with? The hydrogen off of our carbon to make the elimination product. For it to do that, what we're saying is that that hydrogen is the most positive hydrogen in that structure. Is that true? No. No. What hydrogen is the most positive? The one on the oxygen. So adding a strong base does not do the elimination. All that does is convert our alcohol into the negatively charged oxygen. Okay, which actually prevents the elimination because now our leaving group is horrible. So a strong base does not work. Okay, which brings up our other issue. Do we have even a remotely good leaving group? No. So what do we have to do? Make it a good leaving group. How? We could add H2SO4. Why not something like HCl or HBr? That gives you a nucleophile. The nucleophile ends up doing the substitution. We don't want a substitution here. We want the strict elimination. So if we add the H2SO4, we can convert our alcohol into a good leaving group. Okay? And if we give it enough heat, we can end up causing our elimination reaction and we can get our double bond. Okay? Is this our product? No. Okay? So we've got, again, go back and focus on where our chemistry is located. We're getting closer. Our chemistry is now at one of those carbons, but not the other. So what can we do? Eliminate where?
Like, why do you have the pi bond on the right? Why wouldn't it be where you eliminate the OH?
Are those structures different? So the example I would run through is, what's my name? Oh, come on. Okay, we can get some help. What's my name?
Mike.
Did my name all of a sudden change? Well, probably my back is turned, so it's not completely turned. Does my name change? No. Does it change now? No. Doesn't matter which way we rotate the structure. So the rotation of the structure is fine. Okay. If you said something else, we might go down a different path. But the rotation isn't an issue. All that's happened is rotate. And what you'll find is on the ACS exam, they will rotate your products. Okay? They will not put things in, you just add these two together and magically you get the product. They'll add the two things together and they'll turn it upside down and flip it around so that it now looks dramatically different. It's still the same chemistry. You have to focus on not how the structure has appeared to move, but where the chemistry occurred. Okay. So what could we do now? We still need to get the chemistry to move positions, right?
Yep.
Can we get the alkene to shift its chemistry over to another position? Not like that. So what could we do? Said another way, do we want chemistry at that terminal position? No. So what could we add to this to kill that chemistry?
Hydrogen.
Put on a hydrogen. If we put on a hydrogen there, what charge does our other carbon become? What charge hydrogen would we be adding?
Positive.
H plus, which goes to this carbon, right? That terminal one. And it goes to that carbon because why? What charge does that carbon hold? A negative, which means our orange carbon is positive. Okay. What could we put at that positive position? We can't move the pi bond in without breaking some other bonds, and we don't have the ability to break those yet.
A nucleophile.
We can put in a nucleophile. What nucleophile do we want to use? Okay, perfectly acceptable with that. So you're adding H plus and Br minus, also known as HBr. Sorry, I'm going to have to rotate it again. I try to avoid doing the rotation because of the issue that you brought up, but sometimes just the way I draw it. So we've got a new product. Chemistry is there, and we've lost the chemistry off the methyl. Good. We're still progressing closer towards our answer, but now we need the chemistry also at that other position. What's that? Okay. By doing what? An elimination reaction. If we do that elimination, we can now generate that double bond inside the ring. Okay. When we go through and do this elimination, what do we want to add? No, peroxide's for substitutions or additions. It's for radicals. We're not doing a radical. A base. We want to add a good base. What base should we add? Okay. We run into some issues here. If we add OH minus, that is small, which could mean it acts as a nucleophile, which means we could run potentially a substitution. Okay, but it's a strong nucleophile, which would mean SN2. Can this substrate do SN2 reactions? The substrate can't do SN2 reactions because SN2 requires a primary or secondary substrate. We have a tertiary. So we don't have to worry about that substitution. Okay, we wouldn't expect an SN1 mechanism because we have a strong nucleophile. Okay, so that really only leaves us with the elimination. As far as adding a bulky base, what's the issue if we add a bulky base? It'll put the double bond back to the other position. We get the Hoffman product with the bulky base. So we don't want to use something like LDA or the terp butoxide or DBU or DBN because that'll give us the wrong substitution or the wrong elimination. Okay? So now we've made it to B with 1, 2, 3 steps. Cool, not bad. Now 2 more steps to get to that final product. Okay, so again, we can go through and try and evaluate our reactivity. We've got reactivity at 2 positions in our product. Well, I mean 2 carbon positions in our product. Go through and look at the carboxylic acid and the alcohol, hydrogen. Okay? But if we focus on the carbons, why is that nice? I've got reactivity at 2 carbons in my product. Where's the reactivity in my starting material? 2 carbons. Interesting parallel. How many carbons are in my product? How many carbons are in my starting material?
6.
Interesting. Carbons all count out the same.
Okay.
Really the only addition, or the only difference, is that we got a bunch of oxygens in here somehow. Okay? Is there a reagent that can drop in a bunch of oxygens? We need a really strong oxidizing agent, and there's a couple of them that you can use. chm236 is one we've talked about. I think with that one it needs to be, I think it's acidic. I think it's concentrated, and we have H2SO4. Or, the other big one, not chromic acid, though it might do this, I'm not sure. Ozone. Ozone followed by peroxide. Both of those reagents will take that double bond and stretch it and drop oxygens in. Okay? Because under both those conditions, we're running under oxidative conditions, we will fully oxidize both those carbons. And you'll notice a circle, I'll color a purple carbon, has a hydrogen attached to it. Because we're under oxidative conditions, what else goes on to that carbon? ROH. Okay. Yes, that looks god-awful and ugly to look at. So if we're nervous about that, what can we do? Stretch it out and turn it into the nice linear shape, and what do we notice? How do I draw this? That's looking an awful lot like our product. What's the one issue? We have 2 carbonyls, and we only want 1 in our product. 2, 3, 4, 1, 2, 3, 4. Yeah. So what can we do? We have to reduce it. What reducing agent do we use? We'll use the sodium borohydride to go through and do the reduction. The sodium borohydride will react selectively with our ketone, not with the carboxylic acid, and we can convert our ketone down to our alcohol. Okay? 5 steps. Lots of individual pieces to that. The one that I thought was really hard was that permanganate or ozone reaction. Okay? You are officially still responsible for that. So you do need to review that material from first semester for your ozone additions. Okay? Questions about it?
H2 and the palladium to do the hydrogenation on that, would it do both?
It's going to do both. It'll take out the carboxylic acid as well. Okay, so you got the right idea of the reduction, but it's going to take out the carboxylic acid. Okay? So you have to start processing each of those individual pieces. Just for future reference, I'm going to try and make sure each of our lectures starts with a synthesis question. And I will try and include within that synthesis question the functional groups we're looking at and some of those reagents as well, to give you some of that practice. I will probably also start throwing it out there as a quiz. When it comes to this quiz, all I'm really trying to get out of it is to see what you're thinking about and what you're going through and doing, and seeing if I can then come back and change the lecture to fill in gaps that you're missing. Right? So the quiz that I just got, everyone that's did it should have a 5 on it unless you wrote just your name. If you wrote just your name, I'll probably give you 4 points. Okay? How many people didn't write their name on it? Okay, I've got it figured out. It's okay. Okay? So, future reference, write your name on your quiz. So, we talked about our substitution and ultimately our eliminations. That problem actually went through and did a sequence of substitutions and eliminations. We'll look at another reagent, our thionyl chloride. Okay, this was one that we said really, really stinks. One of the things that I'm trying to get you to do is to start thinking about how individual reagents can potentially work. So when you look at a problem like this, if we haven't specifically talked about it, this is from, it's not in the new Post-it, it's the old Post-it. Everybody's complained about me having duplicating slides. So this is carryover from slides posted on Monday. What we want to go through and do is focus on what can potentially happen. So when we look at our alcohols, you should go through and say the alcohol has what reactivity associated with it. So a hint, we've got a positive hydrogen, a positive carbon, a negative oxygen, positive hydrogen. Okay? Which means if I'm now looking at that alcohol, I might say odds are my alcohol functional group will act as a positive. Because there's 3 places for it to be positive, and only 1 place that it can really act as a negative. Right? Until we know what we're reacting it with, we don't really know. So now we can go to the thionyl chloride. And you look at the thionyl chloride, what do you see? What's that? Okay, you see a lot of negatives out on the chlorines and the oxygen. Can the chlorines act as nucleophiles?
Yeah.
Is chlorine willing to share its electron once it's already got a bond? No. Chlorine really can only form 1 bond, which means what about those negatives on those chlorines? They're not useful. So we can eliminate those as possible negatives. Right? The next issue is the negative on the oxygen. I agree. That is a potential site of negativity. But what else is present? Positive on the sulfur. Okay. How positive is that sulfur? Why very?
Because the chlorines are there.
We've got electronegative chlorines drawing electron density away. So the sulfur is now screaming for electron density. Where can it get that electron density the quickest and easiest? From the negative oxygen that we attach to it, which means what about the negative oxygen? It's not very negative because it's trying to stabilize that positive sulfur as best it can, which means after all of this breakdown, what did we find in thionyl chloride? A positive. What does that mean we need to find in the alcohol?
Negative.
A negative. What do? Hook them up. Okay. Our sulfur has now accepted electrons, which means it exceeds its octet, so we'll break a bond. The easiest bond to break, the pi bond to our oxygen. Okay. Once we've formed that intermediate, the pi bond can then reform and kick out a chloride. Okay. I don't remember how far I showed that. Okay. So that pi bond is something that breaks and very quickly forms again because we have a really good leaving group in the chloride. So what ends up happening, we add the arrows back into our structure. Our oxygen attacks, we break the pi bond, we reform the pi bond, and we kick out the best leaving group, which is our chloride. What we end up with is the structure then drawn. Depending on the reagent conditions, we might also see pyridine added, abbreviated PY. If pyridine is present, it goes through and it can act as a base, pull off the hydrogen on our oxygen to put a lone pair, then onto our oxygen. I'm seeing some questionable looks. Fire away. What's the question? No questions? Okay, because we're about to lose all the arrows again. Can I lose them? Call that a yes. So we end up with this structure. This species is now a pretty darn good leaving group. And we'll look at why it's a good leaving group in just a second. Because it's now a good leaving group, the oxygen can be kicked off by a nucleophile. What nucleophile is floating around in solution now? Check that again. Chloride. Thank you. Okay, we're looking at the negatively charged chlorine atom, which is chloride. That can then come in and do a backside attack and kick out our leaving group. Okay? We'll notice that for the thionyl chloride to work, it is doing a backside attack. The chloride is doing a backside attack on our carbon. This is an SN2 mechanism, so we get the SN2 dynamics behind this. Okay? Is there a question there?
Isn't that like horribly hindered though? I mean, there's a lot of stuff.
So
in carbon.
realize in this case, okay, and we talked about this yesterday when I drew out that starting structure, that I have not specified what those atoms are.
Oh, okay.
Okay, those are not to be assumed to be methyls.
Okay.
And in fact, for the thionyl chloride to work, it has to be a primary or secondary alcohol. The tertiary does not work very well because of this steric hindrance. Those aren't specified as those are anything. So that's why I haven't specified them as an R group. Okay, so if those are carbons, we have a tertiary alcohol. This reaction is incredibly slow to the point that it doesn't occur. If it's primary, this reaction happens wicked fast because we perfectly match the SN2 dynamics. Okay? So our first step, I see you, I'll get you in a second, was an activation of our alcohol. Okay, the second step was an acid-base, maybe balancing. And then the last step is really our SN2. Okay, so we're still pushing the same reactions we've seen. It's still a substitution reaction. But before we can get to the meat of our chemistry, the SN2 reaction, we actually have to make sure we've got a good leaving group. And that's what the thionyl chloride really goes through and supplies, is it makes sure that we have that good leaving group. All right? Question, Sarah?
I was wondering if we saw the thionyl chloride with a tertiary carbon, would we just put no reaction?
Specify no reaction. You probably will not see it with that. We'll talk about where you will likely see thionyl chloride show up. Okay. So why is that such a good leaving group? It is bulky. That can be a possibility here.
Stable.
Sort of. We push electron density in, yeah, we could break that pi bond. But is there a good leaving group?
No.
What is that symbol?
Oh.
Chloride. What happens? You can kick that out. And what we'd be left with, which I believe will show up here in just a second, is SO2. SO2 is sulfur dioxide gas. Our gases tend to be very stable, and that can be kicked out of the reaction. We don't have to worry about any reverse dynamics or any leftover random pieces to worry about. The only thing we do have to be kind of nervous about is that this reaction, while giving off that gas, the gas happens to be really awful smelling. Okay? So that sulfur dioxide gas is horrible. So what we've done is just a substitution where we've traded the OH, and there's a reason I'm saying OH, for a chlorine. Okay, so the thionyl chloride is that good of an electrophile. In that very first step, remember, we said our sulfur was very, very positive. It is that good of an electrophile that even our oxygen, as a moderate nucleophile, will very quickly and rapidly attack it and initiate this whole chain of reactions. Okay? The dynamics of it is an SN2 reaction. So what would we expect for stereochemistry? If we started with a stereocenter, what should happen to our product? It's an SN2 mechanism, so if we think back to all of the dynamics of our mechanisms, an SN2 reaction has as a complication inversion of stereochemistry. So when we use thionyl chloride, we tend to see an inversion of the stereochemistry. That's one of the key places that you'll see thionyl chloride show up. You won't see it show up in reference to a tertiary substrate because the reaction is so slow that we aren't really concerned about it. What we are concerned about is the stereochemistry of this reaction. Okay? The next thing that makes this kind of even more interesting with our thionyl chloride, well, we'll stick with the inversion for the moment. Our cool chemistry is it works on all OH functional groups. What OH functional groups are there? way to pick the one we weren't talking about, sure. Carboxylic acids and alcohols. So because we've now reached our alcohol chapters when we first talk about it. When we get to the carboxylic acid chapter, we'll talk about thionyl chloride again, because it will replace the OH off of the carboxylic acid as well. Okay? The reason being, look at our carboxylic acid, much less of a strong nucleophile due to the resonance with the carbonyl functional group. But the electrophile of thionyl chloride is that strong that it will react with virtually any weak nucleophile. Okay? Last part about this, I'm kind of sort of nervous about discussing this part. Okay? We've got an extra little mechanism here. What happened to the stereocenter in this extra mechanism? Let's go through. We got a methyl. Let's make sure it's an actual stereocenter. So there's 1, there's 2. There's 1, here's 2. Make that wedged. Stayed the same. Have we seen a mechanism where our stereocenter stays the same? We don't see it for SN2. We don't see it for SN1. It's technically a new type of substitution reaction. Okay? Thionyl chloride is very interesting in the respect that if we choose our conditions very carefully, we can get a retention in the stereochemistry, which is really, really cool. None of our reactions actually allow for that. Okay? That one balance has to do with pyridine. If you see pyridine, okay, that structure up at the top with our nitrogen, also abbreviated as PYR or sometimes even PY, we see inversion of stereochemistry. If that is not in the reaction, we get retention of stereochemistry. Everything I've seen within sapling is pushing inversion. Right? They don't look at this secondary mechanism, which is interesting because everything I've seen says thionyl chloride does this chemistry. I have yet to check the ACS to see which the ACS prefers. Okay? So we have to be careful with what conditions we're actually putting our thionyl chloride in. Okay? We'll either see inversion or we'll see retention. Those are our two options that come out of it.
So if we don't use pyridine, do we have retention?
You have retention without pyridine.
That's because the pyridine just kind of works on the top stuff, so the chlorine comes from underneath.
Yeah.
Kind of blocks the top action.
Kind of blocks it potentially, that our chlorine has to come through in this kind of retention of stereochemistry. It may come down to the fact that with the hydrogen on there, it's not as good of a leaving group. So the chloride can immediately swing in and help push that out, whereas with the pyridine in there, it helps facilitate and make that a better leaving group so that it leaves first-ish, and then our chlorine can come in and do the backside attack. Okay.
Does the orientation have to be that way? 'Cause
The orientation of how I've organized the sigma bond does not matter. The only reason I oriented it that way so that you could see it more cleanly. Remember, we're looking at a two-dimensional plane of a three-dimensional object. Okay? So, lesson from thionyl chloride, substitution. Trade your alcohol for a chloride. Or sorry, your OH for a chloride. Questions? Next one, phosphorous-activation, PBr3. Any guesses? What do you see as far as reactivity in this one? Our phosphorus is very, very likely to be positive because the bromines are highly electronegative, pulling that electron density away from the phosphorus. Okay, that is indeed how this reagent works, pretty much identical in mechanism-ish to our thionyl chloride. Our oxygen goes through and attacks our phosphorus and kicks out the bromine. Okay. You'll notice it may look a little bit weird because our phosphorus has a lone pair. And we say, well, phosphorus with a lone pair could act as a nucleophile like nitrogen. What's the big difference between nitrogen and phosphorus? There's a big hint. There's a big hint. What's the big difference? Okay. Phosphorus is much, much larger, which means, yes, it does have that lone pair, but the lone pair is effectively the same size. It doesn't occupy as much space on the phosphorus. We have the expanded octet dealing with the d orbitals, so that oxygen can still get in there and attack that phosphorus. Okay? Definitely tricky, but that's what's going on. That piece is now a really good really good leaving group. So what else is floating around in the solution? Br minus. What happens? Backside attack kicks out our good leaving group. Okay? So we get kind of the same special issue with our phosphorus. It's really, really big, so we can expand that octet, which is why it can act as an electrophile in this case. Not only that, because it's really big, we can actually do a stabilization between the oxygen and the phosphorus, which we'll see in more detail again later in the semester, to stabilize that oxygen leaving group. Yeah?
What happens to the hydrogen that's bonded to the oxygen?
That goes away with the phosphorus bromide. Yeah. In this case, our good leaving group is with the oxygen being positive. Okay. The phosphorus will continue to react because there's still bromines attached. It's now slightly less electrophilic than it started, but there's still bromines there, so it can be attacked by yet another alcohol, and we can do another substitution, right? Another trade out of a bromine. Yeah?
So what about the stereochemistry? Because we don't see...
Stereochemistry is, again, in this case, an SN2 mechanism, which means what happens to a stereocenter if it's present. We get an inversion in stereochemistry, which we would get in this case. Notice the bromide is attacking from the bottom on this.
I just asked the question because of that special condition with pyridine in the
Yeah, we don't have to worry about that weirdness with the PBr3, or our phosphorus tribromide. Okay, so we'd end up with our inversion and our stereochemistry, and we kick off that phosphorus oxide.
Why
Yeah?
is it considered an activation?
We are activating the alcohol to act as a leaving group. Because if we go to the very beginning, if we just put in our alcohol and Br minus, would we expect a reaction? Nope, because the alcohol is not a good leaving group, so it stays. So we have to activate the alcohol to be a good leaving group. So the first step of our mechanism is our what I've been calling our alcohol activation, to then allow some chemistry happen further on down the road, which in this case happens to be an SN2, a substitution to put on the bromide. Once the bromide's on there, what happens if we add a bunch of heat? We can potentially do an elimination. So we could run to the point where we start with an alcohol, we react it with PBr3, but then we say add lots of heat. What we're expecting as the product is not the substitution, but the elimination, because it does the substitution first, followed by the elimination. Okay, so we'd have to look for clues within the question to help us decide that difference. Okay? So the type of reaction, we're looking at a substitution, and we're running under the SN2 mechanism. And then one last thing on here. Just like our thionyl chloride, phosphorus tribromide will work with alcohols as well. So we can convert carboxylic acid into a carboxylic bromide. Okay? There's a question there, so let me draw that out. So we didn't draw it out for the last one. If we start with a carboxylic acid, let's try and draw a carboxylic acid first. If we add PBr3, we can then convert this into that species. So we can pull the full substitution, bromide for the OH. Okay? Do we need to worry about stereochemistry with this example? Why not? It's an sp2 carbon, not sp3. We don't have to worry about stereochemistry. Good job. Okay, questions? Okay. Last one we'll look at is what's abbreviated as TSCl, and usually pyridine. This is yet another alcohol activation. we're looking at a tosylate activation. So the TS stands for tosyl, and I've got the tosyl group shown just underneath there. You'll notice that I have that little squiggly line present, and that's because the tosyl functional group, if we want to call it that, has a couple different circumstances where it can show up. If we make that little squiggle an OH, whoa, we make that squiggle an OH, what would I expect this species to now act as? I know, everybody's got it. Close. Got the right idea. Let me change up the perspective on this a little bit. We'll do our sulfur. There's our double bond to an oxygen, double bond to an oxygen. We said that side was an OH. What if I did this? What does that species act as? Yeah, a really, really, really strong acid. That's our sulfuric acid. What's the difference between our toluene sulfonic acid or our tosyl acid versus our sulfuric acid? We're looking at a carbon versus an OH off of one end. Okay? So the toluene sulfonic acid is just another really strong acid. It just happens to be an organic acid because it has carbon in the structure. So if that squiggle is an OH, then our species acts as a Bronsted-Lowry acid. And it is referred to as toluene, if I can spell that right. Toluene sulfonic acid. Why? What is this group? Toluene. What is this group? Sulfonic acid. So we put the two together, toluene sulfonic acid. All right, now let's switch it up. Where that squiggle, instead of being an OH, is now Cl. What happens now? For it to act as a base, we'd have to have a lone pair to be able to accept hydrogens. Okay, we have lone pairs on the chlorine, and we have lone pairs on the oxygen. Okay, would the chlorine be willing to share its electrons? No. How about the oxygens? Probably not as well, for the same reason that when we looked at the thionyl chloride, we've got some electronegative groups attached to that sulfur. The sulfur is now very, very positive. So all of that electron density is getting sucked in towards the sulfur. The oxygens can't really contribute. So we're not looking at it act as a base. But in that conclusion, we really just said the sulfur was what? Very, very, very positive. If our sulfur is positive, what does this species then act as? We now have a really good electrophile. What do we have in the case of our alcohol? We have the nucleophile. Why should we be looking for a negative? What did we find in the toluene sulfonic chloride? A positive, which means what do we need to find in the alcohol? A negative. The only negative there is the lone pair on that oxygen. That then acts as our nucleophile. And we do pretty much the exact same thing that we've been doing for all of the others. Okay? Our alcohol can then go through, attack the sulfur. We'll end up breaking the pi bond, reforming the pi bond, and kicking out the good leaving group of our chloride.
You don't have to worry about sterics.
Why do we not worry about sterics? Sulfur and phosphorus both have this characteristic. They are big. We have the expanded octet. Yes, there's a lot of stuff drawn around that atom, but remember, what we're drawing there makes it look like they're all the same size. Sulfur is much larger than the rest of those. Okay. The result or the end product of this is that we end up with our alcohol attached to our, which I'm just going to pretend that's a ring, our chloride. What do we now have in this, whoops, not our chloride, our methyl. What do we now have out here? A really good leaving group. Okay? Not only is it a really good leaving group, but it's very bulky, which would prevent it leaving off on one side and a substrate coming in. So our nucleophile has to come in from the back side, which means, again, what mechanism do we run? SN2. Okay? So we can get some interesting results coming out of this. What is that nucleophile? It could be chloride. More than likely it's not. So the thing that's nice about our toluene sulfonic or our tosyl chloride reagent is that the chloride is in there in relatively low concentrations. So we could add in another nucleophile to go through and kick out our leaving group. Okay? Kind of makes sense? So each of these steps was ultimately trying to activate the alcohol to give us a good leaving group. Once we had that good leaving group, we now have access to substitution and elimination mechanisms. Okay? Questions? Okay. Within our eliminations, we've got the general breakdown on what happens. We're breaking a carbon X bond. In all of these cases that we just went through, where we're talking about our eliminations, that X ends up being a halogen, right? Because we went through and did a substitution with our alcohol to convert it to a halogen. The only case where that wasn't true was the tosylate, okay? Turning our alcohol into that tosyl leaving group. And then we also have to break that carbon-hydrogen bond. With our alcohols, breaking the carbon-hydrogen bond was virtually impossible because we're looking at a base being potentially added to break that, right, which would mean an E2 elimination. So if we look at all our possible options, we're now narrowed down to our E1 versus our E2. For the E2 elimination to occur, we need a strong base. The strong base would react with the alcohol, negating the leaving group ability. So the E2 mechanism does not work for alcohols. We have to run under the E1. Can we still get the E2 to work? In a secondary reaction, we can convert the alcohol to an alkyl halide. Once we're at the alkyl halide, now we still have access to our E2 elimination. Okay? So we end up stringing together a bunch of reactions to try and get it to go through and do it the way we want it to do. Okay? Questions? Those of you that have had me before have seen this summary slide. Those of you that haven't, you should have everything on this slide memorized. Those of you who still had me should have it memorized too. Probably didn't, but you should go through and memorize it, because that's what tells you how these reactions work. Okay, so if you're trying to predict a product and you're trying to decide between the E1 and the E2 elimination, if you don't know the differences between them, you can't predict which mechanism, which means you can't predict which product. Okay? What we're now going to move into is the epoxide reactions. I haven't put any slides together for an ether reaction. I'll probably get that put together for Monday. The ether reaction is kind of boring. You could probably already guess all of your ether mechanisms on your own when making those. The epoxide, theoretically, is a review. There are two primary mechanisms for going through and making the epoxide functional group. The epoxide is where in this figure? Our dead center is our epoxide. Okay. The reason the epoxides show up in the alcohol chapter is once we have the epoxide, we can react it to make what functional group? Alcohol. what makes epoxides even more special is that in the process of doing this, not only do we have the alcohol, which keeps our carbon active, but what happens to the other carbon? We have a nucleophile there, which could very well mean that that other carbon is still active, depending on what our nucleophile is. Okay? So our epoxides are really, really helpful because they can maintain chemistry across 3 atoms or 4 atoms, whereas an alcohol just keeps it across 2. So the epoxides are nice because we got to do a lot of extra things with it. Okay?
How do you get from the very top left one to the epoxide?
So as far as picking all of these out, what we wanted to go through and do is look at each of these. The MCPBA is the one that we talked about in first semester. That's just our standard addition reaction. Okay? That is an addition reaction that goes through and adds an oxygen across the pi bond. All right, so if you remember nothing else, MCPBA, epoxide, done. With what functional group? An alkene. Okay, the upper left one is a little bit tricky. Okay, so when we look at that one, what's happening? Is it just an alcohol? We have the alcohol and we have a halogen. Right, what we have here is what's known as the, anybody remember this one? Halohydrin. Why is it nice, or why is this species particularly useful? If we take a look at our carbons, the carbons in the halohydrin are both active, just like the carbons in our epoxide. Okay. What reagent do we add? We add the strong base. The strong base reacts with and I didn't specify what kind or the structure of it because I want you to just focus on the strong base. A strong base by definition does what? Accepts hydrogens. What hydrogen is it going to react with? The most positive hydrogen. Which hydrogen is the most positive? Why the one on the alcohol? Oxygen is more electronegative than the carbon, which means the hydrogen coming off of our carbons aren't very positive, which means we'll pull off the hydrogen off of our alcohol, which means what charge does the alcohol build or the oxygen build? Negative. What needs to react with the negative? Where's the next most positive thing? The carbon attached to a good leaving group. Okay? And what we end up getting is the intramolecular ring closing forming the 3-membered epoxide structure. Okay? I didn't talk about it a lot first semester because, any ideas why? It's really weird. The sterics of that, being able to force everything down to do that attack, seem a bit odd. So how do we know that this works? You did it in lab and we know it works. Done. Now you have to know it that that's what's going on with it. It's not looking at this and saying, "Oh, I don't think that's going to work." That's a moot point. It's been done in lab. We know it works. So you now are responsible for knowing it. Yes.
Are you showing the one in the middle as a generic one?
As a generic epoxide, and I added a little bit of detail with the hydrogens here, because that's important for the second steps. Okay. So if we take a look at what follows from our epoxide down, okay, what's the difference between the two products generated? So product 1 and product 2. No, they are not enantiomers.
Whether the nucleophile into the most substituted.
The nucleophile attacked a different position. Okay, the only way we would know it was different is if I put in those hydrogens, which is why they're there. So depending under what conditions we run our epoxide reaction, the nucleophile is going to attack a different position. So we'll have to come up with an explanation for why that will occur. Right? And we'll look at that. And it really isn't as bad as you may think, because you're looking at the answer saying, oh, that doesn't make sense. Don't look at the answer, look at the steps that lead up to the answer. All right? So, oh, this was definitely supposed to be hidden. Sorry. So all at once, there it is. This is our halohydrin mechanism. All right? So what ends up happening to form our halohydrin, all right, that's this guy here, partway through this reaction. We can make the halohydrin by reacting an alkene. So this is the reaction you should have seen in first semester with Br2. Right? When we react the alkene with Br2, our alkene acts as the nucleophile, attacks one of the bromines. That chases the electrons further along, and we form a pseudo-intermediate where our carbocation is formed and the bromine's there. The problem with that is the bromine is so large that it actually shares its electrons back down with our carbon structure, and we end up forming the intermediate shown, which is known as the bromonium ion. How do we know this weird thing formed? We go into lab, and in the experiment of our lab, what we notice is that the stereochemistry of our product, our halohydrin, has the bromine and our nucleophile located where? Trans, and only trans. If we did not form this weird bromonium intermediate, we could expect to see some cis product. We don't see it. That necessarily means that we have some weird intermediate like this that prevents the cis product from forming. Okay, so we have to see that trans product form. So again, we run into this issue. Well, how did we know this happened? We know this happens because we went into the lab and we saw that it happened. Now we have to come up with an explanation for why it happened. Okay? So once we form the bromonium, what happens? Does the bromine want to be positive? No. So it starts to panic and grab for electrons. As it grabs for electrons, it starts to form a carbocation. How do we stabilize that carbocation? We need to give it something negative. So we now look into the solution to see what's around that's negative. What do we have? We've got H2O and Br minus. If we did a comparison of which one's the better nucleophile, Br minus is the better nucleophile. So how can I make sure that the H2O is the one that goes on? We use a lot of H2O. So we see a concentration effect in this reaction. The water will end up attacking because we add so much water that we can get the halohydrin acting as our nucleophile, or our water acting as a nucleophile instead of the Br minus. Yes, we end up with a protonated alcohol. We can deprotonate that alcohol, and we've got, or deprotonate the H2O structure, and we'd end up with our halohydrin. All right? If you want the detailed mechanism on that, talk to me after class. It's one you've seen already. The last part is dealing with the halohydrin to the epoxide. We add a strong base. What do bases do? They attack the hydrogen. The hydrogen has too many electrons, so we put those electrons onto the oxygen. The result is that we end up with a negatively charged oxygen. Now the question is, what do we have to stabilize that negatively charged oxygen? We might say, well, there's nothing there, except what happens, we looked at lab and something occurred. So we have to find the most positive thing present, which is the carbon with the leaving group attached. And we end up forming our epoxide. Yes, we have really crazy sterics going on with this, or really odd geometries happening. We really have to crunch that angle down. Okay. The cyclopropane, and this isn't officially cyclopropane, but the cyclopropane-like structure, okay, actually has some odd stabilization because it's so small. It does actually some bizarre stuff. So it isn't that foreign of a concept in actuality. It just looks really, really weird. So it does indeed happen, yes.
Where is that bond coming from where the oxygen is? If that bond connecting the bromine to the ring
That
is
bond?
going, no, the other, near the purple arrow.
This one, how, if they're giving the electrons to the bromine, why is it?
They're not giving them to the bromine. We're taking those electrons and let's expand the structure a little bit. So there's our bromine. These electrons from that lone pair are attacking what?
Okay, that carbon.
The carbon. That then breaks the bond to the bromine.
Okay.
Yes, Thui? We need a lot of water because bromide is a better nucleophile.
So what? If you attach the...
It would attach instead of the water, in which case we don't have a halohydrin. We'd have the dibromo product. So we have to add in a lot of water to compensate for that. Okay? Questions on this epoxide synthesis?
So would you say like H2O excess? If that was on.
No, it's implied. You would just say H2O, yeah.
You just don't really know that.
Yeah, it's one of those things that, yeah, they just assume that you know it. Yes? That is also a contributing factor to it. That bond is now really, really long because the bromine is so large. Is much closer, yeah. So let's ask one more interesting question. If this was your starting material, do we expect the epoxide to form? Would I expect to make the epoxide?
I don't think so because it would have a hard time bending in that direction.
Yes.
Look at our mechanism that we drew with the purple arrows. That oxygen is coming from the bottom of the ring, the backside of the carbon-bromine bond. If we look at the question that I just drew up, if our oxygen tries to share its electrons with the carbon, what does it encounter? The bromine with a bunch of electrons, and the electrons instead stay with the oxygen. So we don't expect to see the epoxide form with this geometry. Okay? Yes?
Do we need to memorize this mechanism?
Define, memorize this mechanism. Are you responsible for this mechanism? Absolutely.
Yes.
So, memorizing any mechanism is an awful idea. How did we go through and solve this? We looked for the reactivity of each of the individual pieces. So if you want to go through and memorize the mechanism for every single reaction we've done, remember, we're looking at 3 pages just from first semester of reactions. Okay? Now tack on the experiments that we've done here, we're looking at another 2 pages just so far in the semester. You can absolutely memorize all of those mechanisms. The issue you're going to run into is what you will memorize is not the reactivity, but the structures. The structures will change for every single question you run into, which means if you've memorized this page, when I change the structure, you get the wrong answer because you memorized this page, the structures, not the chemistry. So what we're talking about as we go through and look at each of these is talking about the chemistry. You need to focus on the chemistry. What happens if I go through and draw on another carbon structure out here? Let's throw in a benzene. Actually, you know what? Let's tie that benzene back to it. Does that affect the epoxide formation? No. So what does that mean? We go through and we draw that weird stuff at the very end of this too. that's what I drew, something like that. Okay. But if I change the structure, everybody tends to look at it and go, oh my God, it's an entirely new question. No, the chemistry is the same. Focus on what we're talking about as we go through and address this. So when we say, what did if we go all the way back to this slide that actually had it nicely on it, if I make the squiggle an OH, then what does the species act as? How did we decide that? We evaluate at each and every single one of those atoms what possible charges show up. Based on those charges, what things potentially cancel out and neutralize the reactivity, what things don't cancel them. Right? If you understand the chemistry, there's no memorization. There's some, but it's very, very little. What you end up memorizing are the exceptions to those mechanisms.
So is there going to be a lot on the next test about the actual formation of epoxides, not necessarily
I don't know what you mean.
what we just went through?
Are you responsible for knowing the mechanism? Yes.
Or is it gonna be-
What mechanism am I going to ask you to have on the exam? I don't know that yet. Yeah. When it comes to a mechanism, and this is the next thing that people tend to panic about, if I'm asking you to provide a mechanism, none of these are good examples. Shoot. Okay, none of those are good examples. Let me go back. They're there, because that's our next slide. If I'm going to ask a mechanism, so here we go, mechanism, dun dun dun, mechanism for do I ask that question? I have never asked that question, and I never will. What would I ask? What's the mechanism? Now you go through and try and figure it out. Okay? At no point will I ever expect you to predict the product and give me a mechanism. What I'm trying to do by showing you the mechanisms and working through it slowly is identify the sites of reactivity. Because when you see a question, that's what you're looking for. So if I drew this structure out and drew on a big old honkin', there we go, loop-to-loop chain out there, 90% of the time, students look at that big, giant, squiggly mess and freak out and say, I have no idea what's going on. Well, do you see any chemistry out there? Have we talked about how big, giant, squiggly lines react? No. What we've talked about is how alkenes react. Look at the alkene. The rest of it is irrelevant. Focus on the chemistry, not on the structure. Okay? That's why we walk through and look at the mechanisms, is to find the chemistry. Okay? Not to memorize a new mechanism. Because if it's strictly memorization, my job is irrelevant. Okay? That's not why I'm here. I'm trying to show you where the chemistry is. Okay? So, let's focus on some weird chemistry. Looking at the epoxide synthesis with MCPBA. Okay, we'll do this one fast, and again, we'll talk and we'll start here on Monday. Okay, because this one is a weird reaction. We have two possible results out of this, and this slide is pretty awful, but I didn't have time to fix it. We either have a sequential mechanism or a concerted mechanism. You'll notice in this case there is no difference between the products of the sequential versus the concerted, which means what should we do? We aren't going to be able to tell. There is no difference. So let's change it. Okay. If it's concerted, where is that R group going to show up? If it's concerted, what does that mean? What's the change? What's occurring? What's changing as we go from left to right? The pi bond's breaking, and we're making 2 sigma bonds. What did we say about breaking pi bonds? Ignore it, because a pi bond can be drawn as resonance of a positive and a negative. So we don't need to worry about the pi bond breaking. What we need to worry about is the formation of the sigma bonds. There were 2 sigma bonds formed. Did those 2 sigma bonds form at the same time or different times? If it's concerted, they happened at the same time, which means what happens to the R group? It's going to be permanently in the same space. If it's sequential, what would happen? We would expect 2 products. One where the R group is aimed the other direction. How do we decide which one works? And you figure out what your product is by going to lab. All of these things were discovered in lab. Once we now know the answer in lab, lab says it's concerted, which means we do not get that top result. That's what the giant X was. Okay? So if we look at our R group, the R group stays in the same space. Let's add a little bit more information to this to make it jump out. Let's add another R group that's purple. Where would that purple R group show up in the product? On the same side as the other R group. So what if I switch this up and said, actually, you know what, I'm going to trick you. I'm going to draw the product where the R group's there. Where does the purple R group show up? On the back side. Why? Because it's a concerted mechanism. We cannot rotate about that pi bond. The R's stay in the same relative position. How can we explain that with a mechanism? That means that our oxygen bonds must be forming all at the exact same instant. And this mechanism is god-awful ugly, but fascinatingly cool. The only reason we can come up with it is because we look at the results and we see it's concerted, which means we take the electrons from our oxygen and form a sigma bond with one lobe of our p orbital, which then means that carbon has too many electrons. So what does it do? Pushes the electrons back out towards the oxygen. But now the oxygen has too many bonds. So what happens? It kicks out a bond. Why does it not kick out those electrons? The oxygen is more electronegative, which means wants them more. All of that's good. What we refer to the oxygen as, it is a better leaving group than the hydride. But now what happens? Now this carbon has too many electrons, so what happens to it? We break another pi bond. Okay? We still have too many bonds on our bottom oxygen, so the lone pair on this oxygen comes down, attacks the hydrogen, and pushes the electrons finally back onto that oxygen. Holy Mother of God. Yes, you make a carboxylic acid at the same time as you make the epoxide. How do we know this works? That's what our product gave us. This is what we decided explains that result. That's what we're trying to show you here. Is this one way tricky? Yeah. This is why we walk through this one and tell you what the result is and give you the explanation for why it's there. This is what we think is happening within this epoxide. Why? Very likely because this bond between the oxygens is what? What would you describe about that bond? Is it strong or weak? Why is it weak? Both oxygens are very electronegative, making that bond very, very weak.
Because don't they hold the electron density?
They're trying to hold that electron density. They're fighting with each other over those electrons, and they don't really have a better place to get them. So that makes that bond exceptionally weak and very easy to go through and break. That's the big part of this, why this reaction works the way it does. Okay? So, epoxide synthesis with MCPBA, really what you need to know is that it's a concerted mechanism, which means the R groups, whatever groups are attached to the alkene, maintain their stereochemistry in the product. Last issue, how many products do you get? Why two?
Because you can get like both ways.
What do you mean both ways?
Like you can get like either both dashed or both wedged.
Right idea. Why does it come back to the mechanism? Where did the oxygen attack from? The top of the p orbitals. What do p orbitals also have? A bottom. We can form the epoxide on the bottom side of this as well, which means we do get two products. The relationship between those two products is not cis and trans. They're enantiomers. Okay. Which is the complication of all alkene addition reactions. We get enantiomers, okay, because of those p orbitals. Okay, I know.